Hello dear students, this is grade 11 mathematics lesson on Unit 2, rational expressions and rational functions. On today's lesson, we focus on rational equations and graphs of rational functions. So, after revising this lesson, you are expected to solve rational equations and draw the graph of rational functions. So let's continue to the lesson. Now first let's see rational equation. A rational equation is an equation that can be reduced to the form p of x over q of x equal to 0, where p of x and q of x are polynomials and q of x is different from 0. P of x over q of x equal to 0, where p of x and q of x are polynomials and the denominator q of x is different from 0. So, to solve rational equations, you have to follow the following steps. 1. Factorize the denominators and determine their LCM. After that, restrict the values of the variable that make the makes the LCM equal to 0. So you have to restrict the values of the variable that makes the LCM equal to 0. And multiply both sides of the rational equations by LCM and simplify. After that, solve the equation. And finally, check the answers against the restricted values in the step 2. Any such value must be excluded from solution. The restricted value must be excluded from the solution. So these are the steps. Now let's see example for this. Here, solve x over x plus 1 minus 1 over x is equal to 1 over x squared plus x. To solve this, first I need to factorize the denominator. So you have this one, x over x plus 1 minus 1 over x, this equal to 1 over x times x plus 1. Factorizing the denominator, this 1. After this, find the LCM of the denominator. So the LCM will be x common, you can take one of the two, x times x plus 1 is also, we have as a common, you can take x plus 1. Therefore, the LCM of this expression is this, the denominator. The LCM of x plus 1, x, and x times x plus 1 is this, x into x plus 1. After this, you multiply this expression by x into x plus 1. Before that, let me put the restriction. The restriction, the value of x can take any real number without the values that makes the denominator 0. So the value of x can be any real number, but it cannot take 0 or minus 1. Now let's solve. Multiplying the whole expression by x times x plus 1. So here x over x plus 1, this is multiplied by x times x plus 1 minus 1 over x is also multiplied by x times x plus 1. This must be equal to 1 over x into x plus 1 will also multiplied by x times x plus 1, x times x plus 1. Now let's simplify. When you simplify this, this x plus 1 cancels, x squared is remaining, x times x is x squared, minus x is cancelled by x, the remaining part is only x plus 1. This must be equal to, this cancels by this 1, you have 1. Therefore, this equal to is x squared minus x minus 1, take 1 to this side, minus 1 is equal to 0. Therefore, this equal to is x squared minus x minus 2 is equal to 0. So factorizing this, you have this one, x minus 2 times x plus 1 gives you 0. The product minus 2, the sum minus 1 gives. Therefore, from this, the value of x is, it is either 2 or either negative 1. We have arrived this one. So to put the solution, you have to check your restriction. So from the restriction, you can see that negative 1 and 0 cannot be the solution of this equation. It is restricted. It is excluded from the solution. Therefore, we have found minus 1 here. Since minus 1 is excluded from the solution, we cannot take minus 1. The solution set for this expression is simply, it is only positive 2. Therefore, the solution set for this rational equation, it is 2. Now let's continue to the second example. Let's see this one. Aberra, working alone, can paint a small house in 6 hours. Gannet can paint the same house in 12 hours. If they work together, how long will it take them to paint the house? So let's see this solution. Now before solution, let's see one thing. Aberra can paint the house in 6 hours. Aberra paints in 6 hours. It can complete the whole job in 6 hours. So what fraction of work can Aberra finish in 3 hours? In 3 hours, he completes half of the job, 3/6 of the job. He completes, Aberra completes in 3 hours. In 3 hours, he completes 3/6 of the job. In 2 hours, he can complete 2/6 of the job. If take variable x, in x hour, he completes, where x less than 6, in this case, he completes x over 6 of the job. Again, let's see about Gannet. Let's see about Gannet. So here, Gannet can paint the house in 12 hours. She completes the whole job. If she do alone, she completes the whole job in 12 hours. She can paint the room in 12 hours. So in 6 hours, what fraction of job Gannet can complete? She completes half of the job, or 6 over 12 of the job. She can complete 6 over 12 of the job, or half of the job. In 3 hours, she completes 3 over 12 of the job. So in x hour, she completes x over 12 of the work. Now let's come to here. We are asked if they work together, how long will it take them to paint the house? Let's assume it takes x hour to finish the job when do the work together. So let's assume let it takes X hour to finish the job when they work together. Let it take X hour to finish the job. So in X hour, Aberra completes X over 6 part and Gannet completes X over 12 part of the job. Therefore, in X hour, Aberra completes X over 6 part of the job, and Gannet completes X over 12 part of the job. So the sum of the work together will be 1, or full job will be done when you add X over 6 part of the job done by Aberra and X over 12 part of the job done by Gannet. Together gives you the full job, maybe 10 over 10 or 12 over 12, we don't know. So it is full 1. Therefore, here X over 6 plus X over 12 will give you it is 1. So this is a rational expression. You can multiply this by LCM. The LCM of 6 and 12, it is 12. Multiply by 12 this expression. 12 times X over 6 plus X over 12 times 12 is equal to 1 times 12. Therefore, here 12 divided by 6, 2x plus x gives you 12. 12 by 12 cancel x. 1 times 12, 12. 3x equals 12 means x equals to 4. Therefore, this implies x is equal to 4 hour. Therefore, we have found the value of x, the time it takes to complete the job when they do the work together. Therefore, it takes 4 hours when they paint this room together. This is it. Now let's continue to the next part. Let's see graph of rational function. To draw the graph of rational function, we need to find asymptotes. So let's see rules for determining asymptotes and wholes. Let f of x be p of x over q of x, where p of x is given by ax the power of n plus up to a naught, and the denominator or q of x is equal to bx the power of n plus up to b naught, be rational function, where n is the largest exponent on the numerator and m is the largest exponent on the denominator, or in other words, where n is the degree of this polynomial expression, the expression of the numerator, and m the degree of the denominator. So the graph will have vertical asymptote at x is equal to a if q of a is 0, or it is a value of x that makes the denominator 0 and the numerator different from 0. So x equals to a will be a vertical asymptote if this x equals to a makes the denominator 0 and the numerator different from 0. Okay, in case if this a makes both numerator and denominator 0, the function will have either a whole at x equals to 0 or requires further simplification to this side. Look, for example, if you have this one, for example, if you have 1 over x minus 1, the vertical asymptote for this expression will be this, x equals to 1, because the value of x that makes the denominator 0 is 1. This number cannot make the numerator 0. So the vertical asymptote will be, it is x is equal to 1. If you take this one, x minus 1 over x minus 1 times x plus 1. If you take this one, the vertical asymptote for this expression, the value of x that makes the denominator 0 is 1 into negative 1. But 1 makes both numerator and the denominator. In this case, this 1 is not the vertical asymptote. In this case, the graph will have a hole at x equals to 1. So it will have hole at x equals to 1, and a vertical asymptote will be, for this case, is simply only x equal to negative 1. And it has a hole at x equals to 1, since it makes both numerator and denominator. Now let's see this one. In this case, look, x minus 1 over x minus 1 squared. X minus 1 over x minus 1 squared. In this case, x equals to 1 makes both the numerator and denominator 0. So, but this can be further simplified. So we decide whether it has a vertical asymptote or a hole at this point by further simplification. So further simplifying this, you have this 1 over x minus 1. Therefore, for this case, 1 makes the denominator 0, but cannot make the numerator 0. In this case, the graph has a vertical asymptote at x equals to 1. This is what this sentence say. Okay. Now next, if the degree of the degree of p of x is less than the degree of q of x, or when n is less than m, that means when n is less than m, then the x-axis is the horizontal asymptote of this graph, or the graph has a horizontal asymptote at y is equals to 0. If n is equal to m, if the degree of numerator and the degree of denominator are equal, that means then the line y is equal to the ratio of the leading coefficients a over b is horizontal asymptote for the given rational function. Now the next rule, the fourth rule, if n is equal to m plus 1, then the graph has oblique asymptote, and we can find this oblique asymptote by long division. If the degree of numerator is 1 higher than the denominator, in that case you will have oblique asymptote, otherwise it will not have. It must be 1 higher than the denominator. In that case you have oblique asymptote. The oblique asymptote is obtained by using long division. So let's see example for this. Here we have 3 rational function. We are asked to find the vertical and horizontal asymptote if they exist, and indicate the point if the function has a hole. So the first one, a, f of x is equal to 1 over x plus 2. So in this case, the value of x that makes the denominator 0 is x equals to negative 2. That number cannot make the numerator 0. So the vertical asymptote for this expression will be, the vertical asymptote will be this, x is equal to negative 2. In addition to this, as you can see, the degree of the numerator is 0 and the degree of denominator 1. So the degree of numerator is less than the degree of denominator. In this case, it has a horizontal asymptote. Its horizontal asymptote is this, y is equal to 0. Therefore, the horizontal asymptote for this is this, y is equal to 0. Now let's see B. G of x is equal to x minus 2 over x squared minus 4. To find the asymptote first, let's factorize the denominator, whether this will be simplified or not. Let's see this. So this will be this x minus 2 divided by x squared minus 4 means it is x minus 2 times x plus 2. So from this you can see that 2 makes, negative 2 makes this 0, this expression 0, but it cannot make the numerator. So we have x equal to negative 2 vertical asymptote. So from this, the vertical asymptote, x is equals to negative 2. Let's check for this one. If you put 2 here, it makes 0. Not only this one, it makes the numerator also 0. And when you simplify this, you have only 1 over, you'll have only 1 over x plus 2. Therefore, this function will have a whole at x equals to 2, since x equals to makes both the numerator and denominator 0. So it will have a whole at that point. And when further simplify, you will not have this expression there. Therefore, it has a whole at that point. The graph has, it has a whole. It has a whole at x is equal to 2. And you can also find the point of whole when x is 2. Our function is 1 over 2 plus 1 over 4. It has a whole at x equals to 2 or at 2 comma 1 over 4. It has a whole at this point. Now, next, as you can see, the degree of numerator is less than the degree of denominator. In this case, it has horizontal asymptote. The horizontal asymptote will be, is simply it is y is equals to 0. It will be y is equals to 0. Now, let's see the third example. Now, let's see C. H of x is equal to x minus 1 times x plus 1 divided by x plus 1 squared times x plus 2 squared. So from this, let's see the values of x that makes the denominator 0 but not the numerator. Negative 2 makes the denominator 0 but not the numerator. Therefore, x is equal to negative 2 is vertical asymptote. Let's take another point. If you take another number here, minus 1. If you take minus 1, it makes the denominator 0. Not only this one, it makes also the numerator. So we need to check or further simplify this to decide whether this one is the function has a whole or a vertical asymptote at this point. So further simplifying this, you have this one, x minus 1. So you have x minus 1. This cancels 1 of x plus 1. Therefore, you will have x plus 1 times x plus 2. Again, when you see this one, minus 1 makes the denominator 0 but not the numerator. Therefore, the function has a vertical asymptote at minus 1, not a whole. Therefore, here, not only x equals to minus 2, x is equals to negative 1 is also vertical asymptote. Okay, what remains? Horizontal asymptote. When you see this expression, the degree of this expression is the product of x, the degree is 2. Here, x squared times x is the degree is 3. So, the degree of numerator is less. In this case, it's horizontal asymptote. Y is equals to 0. Y is equals to 0. By the way, if the degree is the same, equal, in that case, for example, if you have this one, f of x is equal to 2x minus 1 over x plus 1. If you take this expression, they have the same degree. Vertical asymptote of this expression will be this x equals to negative 1 because this makes only the denominator 0. In addition to that, it has also horizontal asymptote because the numerator and the denominator have the same degree. So you take the ratio of the leading coefficient. The leading coefficient here it is 2, here it's 1, 2 over 1. In that case, the horizontal asymptote will be y is equals to it is 2. This is it. Now, next, let's proceed. Now, steps to sketch the graph of rational function. To sketch the graph of rational function, reduce the rational function to the lowest terms and check for any open holes in the graph. And then find x and y intercept if it exists. It may not have, or may have, or may not be. So find x and y intercept and find all its asymptotes, if any. It may have horizontal, vertical, or it may have vertical and oblique and so on. So if it has, find its asymptotes, if any. Now, next to that, determine the point of intersection of the graph with its horizontal or oblique asymptote if it exists. By the way, a graph may cross its horizontal or oblique asymptote, but it can never cross its vertical asymptote. And then 5, choose a test point near a vertical asymptote to determine if the function is positive or negative there. This will tell you whether the graph approaches the vertical asymptote in the upward or downward direction. When you approach there, it becomes positive, it moves upward. When it's negative, it moves down. We will see this through example. And finally, sketch the graph. Let's see example. Now here, draw the graph of f of x is equal to x plus 1 over x squared minus x minus 2. So, to draw the graph of this expression, first, let's factorize f of x and simplify if it is. F of x equals to x plus 1 over, when you see factorize this one, it becomes x plus 1 times x plus 1 times x minus 2. Now, let's simplify this one. So, our f of x will be equal to, this cancels, so you have this one. When you cancel this, we have to check whether it has a hole or a vertical asymptote at this point. Since this cancels out, x plus 1, we don't have again x plus 1, so at x is equal to negative 1, it has a hole. But the expression will be this 1 over x minus 2 and has hole at x is equal to, negative 1, at x equals to negative 1, which means it has a hole at which point? Negative 1, comma, our function is this one. We have simplified it. It has a hole at negative 1, comma, when you put negative 1 here, you will have 1 over minus 1, minus 2, minus 3. It will have a hole at this point. Okay, this is the first one. Now next, let's determine the asymptotes for this first asymptote. As you can see, the vertical asymptote for this expression is this: x equals to 2. Vertical asymptote is x equals to 2. 2 minus 2, 0. 2 makes the denominator 0, but not the numerator. So x equals to 2 is this vertical asymptote. And the degree of numerator is less than the degree of denominator. Therefore, here, horizontal asymptote is this: y is equal to 0. It's a horizontal asymptote, y is equal to 0. Okay. Now, third, x and y intercept. X-intercept, to find x-intercept, you make the value of y 0, x-intercept. So, to find x-intercept, make the value of y, this f of x means y, make this 0. 0 is equal to 1 over x minus 2. When you cross multiply this, you get that 0 is equal to 1. This shows that has no x-intercept. Has no x-intercept. No x-intercept. No x-intercept. It has no x-intercept. Okay. Now, y-intercept. Y-intercept simply makes the value of x0 to find y-intercept. So, y is equal to, when you make x0, you will have this one, 1 over 0 minus 2. So, it is minus 1 over 2. Y-intercept is this, minus 1 over 2. Okay, next, check whether the horizontal asymptote, the graph crosses the horizontal asymptote. Our graph is this one, f of x is equals to, or y is equal to 1 over x minus 1, and the horizontal asymptote is 0. So, if you try to determine the intersection of the two, they do not intersect. When you put 0 here, 0 is equal to 1 over x minus 2, it gives you 0 is equals to 1. So, the graph do not intersect this horizontal asymptote. The graph do not intersect. The graph do not intersect. Do not intersect this horizontal asymptote. Do not intersect this horizontal asymptote. So, after this, we'll draw the graph. Let's draw the graph here. Okay. Now, let's put the asymptotes first. Let's divide this to be 1, 2, negative 1, negative 2, 1, 2, again here, negative 1, negative 2. So, the vertical asymptote is this, the vertical line x equals to 2. So, draw the vertical line x equals to 2 with a broken line since it does not cross that point. So, this it is x is equal to 2 is the vertical asymptote, and draw the horizontal asymptote using solid line. It is y is equals to 0, y is equal to 0 is x-axis, so you have this one. This is y is equal to 0 is this horizontal asymptote. So, next, let's just put a point where the graph will have a hole. The graph has a hole at negative 1 comma negative 1 over 3. Negative 1 comma negative 1 over 3 is near here. So, assume this one is negative 1 over 3. It has a hole at this point, negative 1 comma negative 1 comma negative 1 over 3. It has a hole at this point. Now, any intercept, it has y-intercept. The y-intercept is at negative 1 over 2. So assume negative 1 over 3 is here between below negative 1 over 3, below negative 1 over 3. So after this, what you do is you see the behavior of this function near to from the right and from the left. So f of x is equal to our function is 1 over x minus 2. When x approaches to 2 from the right, when x approaches to 2 from the right, this means it is 2 point something, 2.0001 almost. So 2.001 minus 2 is this almost positive number, a very small positive number. So 1 divided by a very small positive number gives you infinity, positive infinity. Therefore, for this case, our function f of x goes to infinity. So from the right of 2, our graph is at infinity. So the curve for this part will be this one. It approaches horizontal asymptote since it doesn't cross. We have checked here. It doesn't cross, simply it's approach for that part. Okay, again, when x approaches to 2 from the left side, 2 from the left side means almost 1.999. If you take 1.99 minus 2, you'll have a negative small number. 1 divided by a very small negative number gives you negative infinity. Therefore, our function f of x goes to negative infinity. Negative infinity. So from the left side of 2, therefore, it approaches its horizontal asymptote, does not crosses. So it moves like this. This will be the graph of f of x is equal to 1 over x minus 2. So this is it. So to summarize what we have seen today, a step to sketch the graph of rational function. So the first step is reduce the rational function to the lowest term and check for any open holes in the graph. And after that, find x and y intercept if they exist, and find all its asymptotes. And after that, determine the point of intersection of the graph with this horizontal or oblique asymptote. Finally, choose a test point near the vertical asymptote so that to see the behavior of the graph near to that point, whether it's upward or downward. After that, sketch the graph. So this is all about today's lesson. Please read examples on page 52 up to 53 and 60 up to 64. In addition to that, please try to do exercise 2.6 on page 53 and exercise 2.7 on page 64. This is all about today's lesson. Goodbye until next lecture.